Hey, well, we got to prepare for liftoff today. We're going to head to space, um, up in rockets and spaceships and things. And to get ready, we're going to play a fancy game of tug of war because nothing gets you ready for trip to space like tug of war does. Yeah, that doesn't make any sense. All right, never mind. So here's the situation. I'm going to have you guys calculate a direction angle, x component, and a y component for each of these three vectors. Um, in the picture, you can see there's a blue vector, a green vector, and a red vector. So measurements are given. They all have magnitudes. That N stands for Newton. It's named after Isaac, not Cam, and it is a measurement of force, commonly used in um, physics and every country in the world that's not the United States. It's a metric thing. Anyway, so you don't need to do anything with the N, just it's the units. You keep it labeled on there. It's like pounds or whatever. Okay, I'm going to be quiet. You can hit pause on the video until you got those direction angles and components calculated. All right, welcome back. So nice work on those. The blue vector is pointing straight to the left, and so that is going to have a direction angle of 0. The green vector is measured at 120 degrees, and that 120 degrees is measured from the positive side of the x-axis, rotating counterclockwise, 120 degrees, bam, green, right? So that is the direction angle of 120. The orange vector is 100 degrees, but measured counterclockwise, also starting from the positive side of the x-axis, but rotating the other way to get to the orange vector. My arm doesn't quite bend that far. The green one, we rotated clockwise, but the orange one counterclockwise. So we're going to subtract. That would be 360 minus 100 to get a direction angle of 260. And then once you got the direction angle, calculate the components by taking the magnitude, multiply by the cosine of your direction angle for the x component, and for y, it's the magnitude multiplied by the sine of your direction angles. We've got to find the direction angles first. Okay, I wrote them down already. Here they are. And I kept my labels on the components. So if you're not coming up with those same components, warning, warning, Will Robinson, warning. You got to go back and check something out there. So talking about adding vectors, and so we're going to use the problem we just started here, but we're going to be able to find the direction of the resultant, also the magnitude. Also, in order to do either of those two things, we're going to have to find the component form of the resultant. So really, there's more to it than just finding the direction. Okay, so there's actually a story behind the picture that you just were working with. This figure shows a diagram of 3 ropes being tied together in a giant knot, and you got a 3-person game of tug of war with a blue person pulling the blue direction, a green person pulling the green direction, an orange person pulling the orange direction at these different forces. And our job is to find the resultant force. If we add all 3 of those vectors together, what is the magnitude and the direction angle of the resultant force acting on that knot? Okay, well, let's look at the diagram for a second. So we could do vector addition. I've got a nice drawing I can manipulate. So if I was to take let's go in order. If I was to take the green vector, and instead of drawing it where it actually is, acting in that rope that's tied to the knot, if I add the vectors together graphically, that might give us a better sense of what our answer should look like. So if I put the green vector at the tip of the blue vector, so I can go tip to tail or head to tail, so blue first and then green, and from the end of the green one, I'd have my orange one, right? And so the resultant looks like, I mean, I'm not even sure I drew these to scale, but it doesn't look like there's going to be much of a resultant if my drawing is accurate. And I can't verify that I've actually drawn this to scale because honestly, the length of this orange vector at 8 newtons looks like it's actually maybe a little bit shorter than the vector I drew for this green one, which is 5, and the blue one is kind of the same length, but it's only 3 newtons. This is definitely not drawn to scale, so I'm not sure how reliable that really is, but maybe we'll try again. Let's shorten up that blue one, and we'll just start a new graph over here. then that's too long for a 5 Newton vector. Maybe like that. And then we can get this orange one at the end. This looks a little bit better. It's still not completely accurate. I didn't measure any of those, but at least closer to scale. So if I was going to make a more educated guess based on scale drawing, I'd say my resultant is going to point over here somewhere, and I'm not going to rely on the accuracy of my drawing to say, well, that's definitely the answer. But it looks like this is probably going to be over here in quadrant 3. Yeah. All right. Well, let's do the actual numbers. Okay. So we've already calculated the x components and the y components. Okay. We use the direction angle to find the components. We're not going to use the direction angle for adding them together. So in order to add together the components, so I'm going to get the resultant. So I'm going to add the x's together with the x's. Find the total of the x components. And I'm going to add the y components together with the y components. That will give me the resultant y component. And I did that already. I wrote them down over here. So I add 3 and negative 2.5 and negative 1.4, and I came out with a total of negative 0.9. That's the resultant x component. I added my y components. I got 0 plus 4.3 and negative 7.9. I got a total of negative 3.6. That's the y component of the resultant. Yay! Okay, next, we could do this in either order because really they're independent. So we need to find the magnitude. We need to find the direction angle for the resultant. All right. I'm going to go ahead and do the direction angle first. You could do either one first. When we do this, I'm going to take the components of the resultant. This is the only thing I'm working with at this point. All of these pieces, the green and blue and orange, I'm done with those. Right. So to find the angle, always use the y component as the opposite side. X component is always going to be the adjacent side. Them's the rules. You can see in my illustration, I drew kind of the components of the resultant. So my x component of negative 0.9 is going to go towards the left on my graph, and the y component, negative 3.6, that's going to go down on my graph. I did draw in the resultant to finish up my little right triangle. Use my little graph walker, keeping track of things. Graph walkers always start at the origin in these vector triangles. So the 0.9 is the adjacent. That's always going to be the case. And not that number, but the x component always is adjacent. Y component is always the opposite. So I set up my tangent ratio. Tangent of the mystery angle is going to be negative 3.6 divided by negative 0.9. And in order to actually get that angle, I will have to backwards engineer this using inverse tangent. So first I divided negative 3.6 divided by negative 0.9. Then I got my inverse tangent on my trusty calculator, and that gives me a 76-degree inside the triangle angle. Okay, so this little theta that is drawn in my diagram, that's 76 degrees. That is not a direction angle, right? Direction angle has got to be measured from the yellow highlighted part of the graph, and then we would rotate counterclockwise all the way around to here, right? So if the portion inside the triangle is 76 degrees, how did I get all the rest of this stuff up here, right? That's an extra 180 degrees. So to get from the positive side of the x-axis all the way around to the negative side of the x-axis, 180 degrees, plus another 76 degrees right here to get to where my vector ends. So I'm going to add the 76 plus 180 to get a direction angle of 256 degrees. Yay! And if there were decimals, I would keep track of my decimals, according to what the directions say. I had 76.0, so I've just left off my significant figures, which probably is bad practice, but it's a 256.0 because this was 76.0. And then let's go back to these components in red, the components of the resultant. I need to use those to find magnitude, right? So magnitude is essentially the length of the hypotenuse of my little vector triangle here. It is the length of the resultant vector, or in this case, the amount of force total acting on the knot in the game of tug of war. I pull it this way and pull it that way and pull it that way, and all together, like you add those together, and the resulting force, so to speak. Oh my gosh, it's like a pun. Is what the magnitude is. So I can use the Pythagorean theorem. I got a side, I got a b side. A squared plus b squared equals c squared. Or I can just start it with the square root of a squared plus b squared is going to give me the length of the hypotenuse. So negative 0.9 squared, add that with negative 3.6 squared. Just point of order here. If you're typing this into your calculator without the parentheses, you're going to end up with negative numbers because your calculator and negative numbers and squaring them doesn't always work the way you think it ought to. So we're going to pay attention. Negative 0.9 squared should give me a positive value. Negative 3.6 should give me a positive value. If I add a positive plus positive, it gives me a positive value. Right? If we don't do that, you're going to end up with a negative value here, another negative value here. You add the negative gives you a negative total, and then you have a negative inside the radical, and that's not possible. We're not dealing with imaginary numbers here. So if you run into an error, use parentheses on your negative numbers, please. So my magnitude, now they got it all entered in my calculator correctly. Magnitude positive 3.7. Magnitudes will always be positive. That's a rule of thumb. Okay, always, always, always positive. It doesn't matter if your components are negative or what. The magnitude is a length, and when we measure length, it's always going to be positive. Think of rulers. We use rulers to measure length. Rulers don't have negative numbers on them, right? Only positive. You can point the ruler in this direction or that direction. It's always positive. Okay, so magnitude should be positive. All right. Hey, so you are now ready to blast off into space and work on the spaceship problem. Woo! All right, I'll see you in outer space.